In this video, I'm just going to go ahead and go over the derivatives in problem 1 of the worksheet. So hopefully these are not too difficult, but let's go ahead and do them. So for 1a, we have y equals x to the 12, and if you're trying to find dy by dx, which is the same as y prime, if you prefer that notation, that's okay. We're just doing the power rule, so you take 12 down in front, and then we have x to the 11. Okay, so that's not too bad. In part B, we have another power rule, except it looks funny because there's pi's and e's. So pi is a constant, so we're just going to leave it in front and not do anything with it. And then dy by dx, we're going to take e down in front, so we'll have pi times e, which looks kind of funny. And then x to the, we need to still subtract 1 from the exponent, so e minus 1. So it's about 1.718. Doesn't really matter, but the most precise way is to leave it as e minus 1. Okay, for part C, we're still doing power rule, but it's looking more complicated. So if you have a cube root, that's like taking a power of 1/3, right? So let's just mess with the original for a minute before we take a derivative, which is sometimes advisable. Okay, so I'm going to distribute that power. So it's going to be 2 to the 1/3 times x to the 5/3. And now I'm ready to take a power rule. So 2 to the 1/3 is going to be a constant out in front. I'm going to take this power down, so 5/3 will come here. Then I'm going to subtract 1 from the exponent. 5/3 minus 1 is 2/3. So that's that. And Dr. Ostroff says he doesn't care that much about simplifying, but I think it looks better if we write this back as 5 times the cube root of 2 over 3 times x to the power of 2/3. If you want, you can write it as the cube root of x squared. That's the same thing. You don't have to write it that way, but I do want you to know that, like, you should be comfortable with this. Whether or not you do it in the problem, I don't necessarily care. But if someone else writes those, you should be able to identify them as the same. Okay, part D, we now have inverse trig functions. I don't like to memorize the derivatives of inverse trig functions. I like to take sine of both sides and then differentiate implicitly. That way I just have fewer things to memorize. I don't like to memorize anything if I can avoid it, except for things that are important, which I will tell you throughout the quarter. So let's take derivative of both sides with respect to x now. Sometimes I write this to remind myself what I'm doing. Taking derivatives of both sides with respect to x. Now the derivative of sine y, now we're going to use the chain rule. So this is cosine y times derivative of the inside, which is dy by dx. And then derivative on the right is just 3, because derivative of x is 1, or x to the 0. Okay, so actually this is really nice. If they let you leave it this way, it's great. But sometimes they want it in terms of x. Okay, so what's going on? Okay, now this is where you won't like this method. Because now we've got a right angle triangle. The angle is y. The sine of y is 3x. So that means I could have a triangle with the opposite side being 3x and the hypotenuse being 1. So by the Pythagorean theorem, that means this bottom side is the root of 1 minus 9x squared. That's the only way that it'll make the sides work out by the Pythagorean theorem. So then the cosine of y is going to be the root of 1 minus 9x squared. So then if I want my dy by dx in terms of x, I'm going to get 3 over the root of 1 minus 9x squared. Okay, so that's a pretty interesting technique. If you're ever somewhere and you forget your inverse trig functions or you just don't memorize them, like me, here you go. You can always derive it. These triangles are good to be able to draw anyways. If you're doing trig substitution with integrals, which I'll go over in a later video because there will be problems on that. So that's good. Part E, y equals 2 to the x plus 2x. Again, I don't like memorizing. Some of you will have the derivative of 2 to the x memorized. I'm going to write it as 2 is the same as e to the natural log of 2. Right? E and natural log are inverse functions. As long as that 2 is positive, we're good to do that. And then this is e to the natural log of 2 times x, right, by exponent rules. So then my dy by dx, I can just know the rule for the derivative of e to the something, which is e to the something. It's the easiest derivative we have. And then I need chain rule. So I need to multiply by natural log of 2. And then I'm adding the derivative of 2x, which is just 2. So then dy by dx, and then like it's fine if you leave it this way, but it's nicer if you write it back. So this is e to the log 2 to the x again, so that's 2 to the x. So if you just memorize this formula and you haven't thought about where it came from in a while, this is where it came from. There's that log 2 times 2 to the x. I'm just going to say log for ln in math. The higher you get in math, the more we assume that logs are base e, not base 10. Okay, part F, y equals cosine cubed x. The derivative, okay, so, and if you have those previous derivatives memorized, this is the first time we're using chain rule. So we're going to take, this is like cosine x all cubed, so we're going to take that 3 out in front, we're going to be left with cosine squared x, and then we're going to take derivative of the inside, which is cosine x, so that's negative sine x. And then I just think it looks better if you simplify this. It looks more like one term. It looks like for sure it's not cosine squared x minus sine x. So, I don't know. Simplifying might be optional in this course, but that looks way better to me. And it only takes a second of your time. Okay, next one. Y equals 4x times log x. Okay, so I'm going to leave the 4 out in front. But then the rest is going to be a product rule. So I'm taking derivative of the first thing, which is 1, times natural log of x, plus the first thing, which is x, times the derivative of natural log of x, which is 1 over x. So I'm going to be left with 4 times natural log of x plus 1. And that can be considered simplified, or if you prefer to write 4 natural log of x plus 4, that's fine. I don't have opinion on which of those is more simplified. Lastly, part H, we have y equals secant x plus secant x. That's fun. Y equals secant of x plus secant x. I don't even have the derivative of secant memorized. So let's just figure out what that is. Or actually, let's just write it in terms of cosines, right? Secant is 1 over cosine. So this is 1 over cosine x plus 1 over cosine x. Okay, I lied to you. Maybe we should memorize the derivative of secant x. So let's just do that off to the side. I went through math not memorizing the derivative of secant x, but I think the problems that you guys see, secant x comes up enough that it's worth it. So if y equals secant x, then dy by dx is going to be, I'm going to derive it one time because I don't know what it is. So 1 over cosine x, this is negative 1 over cosine squared x, because this is cosine x to the negative 1. So I'm bringing the power down in front. The power is now negative 2, multiplied by negative sine x. Okay, so negative and a negative are a positive. This is sine x over cosine squared x. Oh, and I guess what you guys know it as is secant x tangent x. That sounds like something that people say. So I'll do it this way since I think most of you do have that memorized, or had it memorized at one point. Maybe you don't now. Okay, so then we have secant of, and then we're going to do the chain rule. So it's secant of this thing times tangent of that thing And then we have to multiply by derivative of the inside, which is 1 plus, and then we have another secant, so it's secant x tan x. Okay, that's that. There's the answer to part H. You can't really simplify this anymore. Like, I don't know, you could distribute that into that parenthesis, but why? I don't think that's going to be better. So we're done. Okay, so those are all the answers with explanations to problem 1 on the worksheet. I'll make more videos for the next problems.